In this video, we're going to talk about comparing data values from different distributions. And it's going to seem a little bit like we're deviating from our topic, but I promise I'll bring everything together towards the end of this video. So say we have two kids, a 5-year-old and a 2-year-old, and the 5-year-old weighs 40 pounds and the 2-year-old weighs 33 pounds. And I ask the question, which kid is bigger? If I just look at the numbers, of course, I'm going to say the 5-year-old is bigger. But that's not really a good question. It's more of which kid is bigger relative to their distribution, right? Which is the 5-year-old considered bigger compared to other 5-year-olds, or is the 2-year-old bigger compared to other 2-year-olds? So we want to compare these two values knowing that they come from different distributions. So how do we do that? So I'm going to develop this a little bit here, so bear with me. So let's say that we know that the mean for 5-year-olds is 39.75 pounds. So then we know that the first kid, who's 40 pounds, is above the mean. And let's say we're looking at the second kid and we know that the mean for all 2-year-olds is 26.75 pounds. And again, kid 2 is above the mean. So the question is, how far are each of them above the mean? Well, if the distribution is really, really clumped together, maybe 40 pounds is much higher, relatively speaking, from 39.75, then maybe the 33 is if the 2-year-old distribution is really spread out. So we can't talk about how high these are above the mean without talking about the spread of the distribution. And this spread of a distribution then becomes a measurement. So we say that we're using the standard deviation as a measurement. So let me explain further. So say that I know that 5-year-olds have a standard deviation of 5 pounds. Then if I take the mean, 39.75, and I add that standard deviation once, I get 44.75 pounds. So one standard deviation above the mean is 44.75, which means that I know then that this kid that's 40 pounds is above the mean, but less than one standard deviation above the mean. Whereas with the 2-year-old, say I know with the 2-year-olds that the standard deviation is 3.25. If I take the mean and I add that standard deviation once, I get 30. So the 2-year-old who's 33 pounds, they are above the mean, but they're also they're more than one standard deviation above the mean. So now with this information, with the combination of the mean and the standard deviation, I can now look at these two measurements relative to their distributions and say that kid 2 is bigger than kid 1 relatively. But we're going to actually hone this in a little bit more and find what's called a Z-score. So a Z-score is a measurement for how many standard deviations above or below the mean a data value is. And we have this formula right here. You're going to definitely make sure that you have that written down in your notes and available during the exam. So we have our information. So our distribution for 5-year-olds, we have the mean is 39.75 and the standard deviation is 5 pounds. And we have this single data value of 40 pounds here. So what is the Z-score for this data value of 40 pounds? So the Z-score formula means we take that data value, we subtract the mean, and we divide by the standard deviation. And we have a Z-score of 0.05. If we do the same thing with a 2-year-old, so again, we have the mean here, the standard deviation here, and the data value here. If I take the data value of 33 minus the mean of 26.75 and divide by 3.25, we have a Z-score of 1.92. So the Z-scores are measuring how many standard deviations above or below the mean a certain data value is. So both of these z-scores are showing that the data values are above the mean because both z-scores are positive. But for kid 1, the z-score is barely above the mean, whereas for kid 2, that z-score is close to almost 2 standard deviations above the mean. So if we wanted to say, okay, now which kid is bigger relative to their distribution, we would say, again, that kid 2 is bigger. Let's do another example. So say we have, sorry, I lost my little answer sheet here. So say we have this problem. It says, sorry, forget that this says example 4. Although most of us buy milk by the quart or gallon, farmers measure daily production in pounds. Guernsey cows average 39 pounds of milk a day with a standard deviation of 8 pounds. For Jerseys, the mean daily production is 43 pounds with a standard deviation of 5 pounds. When being shown at a state fair, a champion Guernsey and a champion Jersey each gave 54 pounds of milk. Use z-scores to determine which cow's milk production was more remarkable. So we have these 2 cows. So we'll look at the Guernsey cow first. And our data value for both of these cows is 54, right? That's the milk production. So the data value is 54. For the Guernsey cow, the average, the mean, is 39, and the standard deviation is 8. So when we go to find the z-score, this is going to be the data value minus the mean divided by the standard deviation. Just be very careful when you're putting this in your calculator. If you're going to put it in all at once, make sure you put parentheses around the numerator or do it in steps. Take 54 minus 39, hit enter, and then divide by 8. But make sure that you're subtracting before you're dividing. And this will give a z-score of 1.875. Let's do the same thing for the Jersey cow. Again, the data value is 54. The mean is 43. And the standard deviation, it's kind of a weird D. The standard deviation is 5. So again, when we calculate this z-score, we're going to take the data value minus the mean divided by the standard deviation. And put those parentheses and you'll get a z-score of 2.2. So that means that, relatively speaking, we know that the Jersey cow has a more remarkable milk production because its z-score is further above the mean. So we would say the Jersey cow's milk production is more remarkable because its z-score I always put that when I'm not supposed to, because its z-score is further above the mean. So a few notes on z-scores. First of all, if it's a positive z-score, it's above the mean. If it's a negative z-score, it's below the mean. If you have a z-score of 0, that means that your data value is exactly the same as the mean. And the z-score gives the number of standard deviations. So a z-score of 1 means that it's 1 standard deviation above the mean. A z-score of -2 would be 2 standard deviations below the mean. The smaller the z-score, the closer it is to the mean. The larger the z-score, and again, that could mean either positive or negative, but the further away from the mean. So one more thing about this. So I want to connect the empirical rule with what we just learned with z-scores, because z-scores work best for populations whose distributions are approximately bell-shaped, meaning that they're unimodal and close to symmetric. And this was the same requirement for the empirical rule, that the distribution was approximately unimodal and close to symmetric. And because the empirical rule talks about the percent of data that is within one standard deviation, and z-scores are a measure of standard deviation, we can connect these ideas. So we can say that 68% of data will have z-scores between -1 and 1, right, within one standard deviation. 95% of the data will have z-scores between -2 and 2, and 99.7% of the data will have z-scores between -3 and 3. This also means that if you ever see a z-score that's large, and really large, meaning above 3, right? If you see a z-score of 4.6, that is unheard of, right? That is really, really large, and the possibility of observing that is extremely small. And this is also how you can check your math. If you ever get a z-score that's really out there, 67.25, you know that you did something wrong in your math, because it's just not possible. Most of your z-scores are going to be between 0 and in the 3s.